Now, so everything that we have done up to and including yesterday is going to help you with, would be arguably probably the most two difficult days coming up today and tomorrow. But and I'm telling you that obviously not to scare you, but just to make you feel normal when you're going through these things. The one advantage that you will have when you're going through your homework is that you will have all of the problems worked out. The other thing that you will find is that the more of these you do, the more they're the same. Okay? They will seem very unique, every problem to itself. And then after you do enough of them, you will find that they kind of start repeating themselves anyway. Now, it's always nice when you're going through, we're doing word problems today, and we're doing related rate problems. Now, I just want you to kind of understand before we get going, like what are we doing here? Why have we never had to do something like this before? Now, if I was, say, pouring water into this cone, and I asked you after 2 seconds what would be the height, okay, of the liquid in the cone. Now, if in the past you would be doing something like this. Now, what's the difference between these two types of problems? They're both shapes. They're both three-dimensional shapes. When you're filling up the cone, the height goes very quick at first, doesn't it? And then as the cone spreads out, the height goes slower and slower and slower. It's very inconsistent. Well, it actually is consistent, but it is not the same any two places. Whereas when you fill up a cylinder, it's always going to be the same. It's going to be the same rate. The height will be, and that's because the radius is the same all the way through. The radius changes as you move up a cone. So we're going to be dealing with stuff that you just can't pull out the simple formula and plug it in. Okay, you're going to have to be able to find the rate. Okay, and rates come with like velocity. It's a slope. And if you can find the slope at that point, you'll find the instantaneous rate or the instantaneous velocity. So what we're going to do is we're going to write down the steps of how to go through this. It's going to make absolutely no sense to you, but then we're going to do a problem, and I'm going to go, okay, this is like step one. This is what I'm talking about, step one. The other way is do the problem first, and you're lost through the whole problem, and then we go do the steps. Okay? So, okay. So number one, and I'll keep referring to it. We're going to be doing number one now, or number two. Now, you always want to draw, it's like an epidemic in here, draw a diagram part way through the motion. Okay, now this is sometimes called a snapshot. Just right. Okay. Now, and then label all the key variables in the diagram. The more stuff that you can take out of that paragraph and put it onto the diagram, the easier this stuff is to understand. Then you want to list all given rates of change. They may say that the volume is changing at this rate. Find how the radius is changing. Okay, so they may give you some. And rates of changes are derivatives plus the one you are looking for. Okay. And then tomorrow we're going to be doing a little bit more difficult ones. Sometimes there will be one rate of change given and two rate of changes that I don't know, but they don't give me either one of them. And we're going to see how to deal with that. But today, they're going to give us one rate of change, and we're going to be looking for the other one. Okay? Now, 3 is find the equation. This may be one of the most difficult parts. Find the equation relating the variables. So, not only do you have to know what you're learning today, you have to know everything that you've learned up to today in all of your courses, all of your 3D figures, all of your Pythagoras. Okay? That stuff all has to come in, all of your formulas. Now, number 4 is kind of more for tomorrow. If there is a variable that is not on the list, is not in the list or the paragraph, you need to remove it. And it's not as easy as just erasing it, okay? You got to actually remove it mathematically. So how do you do that? Find another equation that relates the variables and the substitutions or the substitutes. And sometimes you can put in constants, and any constants should be put in before the derivative is taken. Okay? And that's going to be the thing you're going to have to decide. Is that changing as I fill it up? Yeah, it is. Okay, so I can't put that into the formula. That would be a rate, right, if it's changing. Okay, number 5 is where we finally start doing some Math 31. Take the derivative implicitly with respect to time. They are rates, so they will be with respect to time. 6 is substitute the values and solve. Now, if there is any values missing, you might have to go back to the original formula before the derivative to calculate them. Okay, so you may have found the radius. So you just got to go back to your original volume formula and put it in there. And then 7, everybody's favorite, express your answer with proper units in a sentence. See? Easy. Now, here is just some examples of some shapes that you'll be looking at. You do have them on your formula sheet, but they don't have the pictures, so hopefully you know what they mean and how they all relate. Now, if you look even on the next page, we've got the good old cone. Okay, so you got your slant height formulas, your volume formula, surface area formula. Okay, so we're going to start off with a nice easy one, very few words, and I'm going to go really slow, and anytime I lose you, just put up your hand, okay? Okay, you ready? So this is a rate of change problem, your very first one. Now it says if x cubed times y cubed equals 8, and it says dx of dt, so x is changing with respect to t equals 3. So I don't even have any units in here to bog you down right now. And y is changing with respect to time, or it says find y dy over dt when x equals 1. Okay, so that's why we were talking about the snapshot, because as that thing's filling, you know, as the cone's filling or whatever, at a certain time, the height's going to be this, and then the next time the height will be this, and the next, so they have to give us the height if you want the, or the time, sorry, if you want the exact height at that time. Now, sometimes you really don't kind of know what you're looking for until you, now we're going to draw a picture for this one. We'll get on that with the next one. But right now we know dx of dt. So you can see when we take the derivative of the x, we have that to fill in there. We also have x, don't we? Okay. And we have, when we do the derivative of 3y cubed, right, we'll have dy, or we're looking for dy dt. You can see that we're going to need what variable to start working with this? Okay, well, let's do the derivative. Okay, you guys remember the old product rule? So this would be 3x squared now we need to always implicitly derive. So this will be dx dt times y cubed plus the first times the derivative of the second would be 3y squared dy dt equals dy over dt is y prime, yeah. I put it in the first one because we're always doing it with respect to time. If I was doing this with respect to x, this would be dx over dx and it would cancel. But because these are all rates, we'll always, when I take the derivative of this, it was 3x squared, and then I have to do the derivative of the inside, which is dx over dt. So you kind of have to do the chain rule when you're implicitly deriving. And then this just came over here because it's derivative of the first times second plus the first times derivative of the second, which is 3y squared, and then inside's dy dt. Why I did it here? Because all the other times we've been doing in the past, if you had, say, find the derivative of x plus y equals 5. Now this one I can, but this would be 1 times dx over dx plus 1 times dy over dx. So that would cancel. But now we're doing, so we never did do it, right? We just said if it's x, just, you know, implicitly derive the y part. So whenever we're doing on these change of rates of change, you've always got to do with respect to t. Okay? Now, and you can see why I made it equal 0. Oops. What's wrong here? Does everyone see why I made it equal 0? Because my derivative of 8 is 0. Now, Here is my unknown. This is what they want me to find. Can I go and solve for it yet? What is stopping me from just plugging stuff in and getting the answer? I don't know why. I know what x is. I can find y from my original formula. Okay? So let's start just numbering things here. So number 1. So number 2, we need to find y in order to solve. So this stuff needs to be logical. Like I just don't want, why is you just always find y second step? No, I know this. I know this. I'm looking for this. I don't know, I know that. I don't know this, right? So if you have 2 unknowns, you can't go solving. You can only have 1 unknown, unless of course you have 2 equations. But I know that x cubed, y cubed equals 8. So 1 cubed times y cubed equals 8. I'll put x equals 1 here. Okay, so y cubed equals 8. Y equals 2. Okay, so now that I know my y, I can solve for dy over dt. The only problem is right now, dy over dt, it's not by itself, right? So let's get this so it is. So why don't I bring the other, so this would be dy dt x cubed y squared, oops, forgot my 3 equals, I'm just going to bring all of this over to the other side. So equal negative 3x squared y cubed dx dt. Now I'm going to divide this out of both sides. So dy over dt equals negative 3x squared y cubed dx dt all over 3x cubed y squared. So dy over dt, let's do some simplifying. Negative 3 divided by, that is negative 1. And then I'll have an x on the bottom and a y up top, dx dt. Okay, now some would even argue at this point that, like, what if the y's would have canceled here? I've wasted all my time here. So some people like to go and, well, I'm going to go get it dy over dt first, and then I'll see what I need, and then I'll come over here. Okay? And that only comes from practice, right? But I guess because I've been through this one already, I'm like, yeah, I mean, but most times it's not going to be nice and cancel for you, but the odd time it does. So now we know all of my numbers. So let's put them in. So dy over dt equals negative 1 times 2, and dx over dt is negative 3 all over x, which is 1. So this equals 6. So therefore dy over dt equals 6. So this was just kind of an introductory to having going through, doing the derivative implicitly, having to go find y because I'd have too many unknowns, getting the derivative dy over dt by itself, and then plugging in everything you need to know. Okay? Now let's really get to what this is good for, and this is for when things are either they're enlarging, or you're filling something and you want to find out what would be the width or height, or what would be the radius at that time. So we had to find the length of a rectangle is decreasing at 1 centimeter per second, and the width is increasing at a rate of 2 centimeters per second. Find the rate of change of area at the moment when both lengths are 10 centimeters. Okay, so can you picture that this thing's in transition here, that the length is getting smaller, the width is getting bigger, so the area is always changing. Okay, when you're doing that, you're messing with the area. So they want to know, well, when would the, what's the area when it's a square? Okay, or find the rate of change. Doesn't even want the area, that'd be too easy. To find the area, you'd go 10 times 10. But what is it changing, right, per time? Now, let's first draw a diagram. Okay, let's call this length and this width. So what's happening here? This is getting smaller as this is getting bigger. And every second that goes by, the area changes. Now let's start just reading through our sentence, because something really important is going on here. And what variables do we know right now? Like, does anybody know? That's why math is actually so confusing, because it takes something that long and makes it, you can put it in one little mathematical expression. How would I write that? The length of a rectangle is decreasing at a rate of 1 centimeter per second. What is that? No, because it's a rate of change. So rate of change is always the derivative, okay? So how would we write rectangle decreasing at a rate? This is the, whenever you have a rate, you will write it as dl over dt equals what? -1. That's huge, okay? Because if you put 1, it all goes bad after that. I mean, you're going to get a lot of marks for work and stuff like that, but you won't get the right answer, okay? So decreasing is negative. So dl over dt equals -1. What else do we know? Yep. dw over dt is 2. I mean, if you want, we can put in the units here, centimeters per second and centimeters per second, right? So we just took 2 sentences already and put them into, just grab the information. Okay, so we know that, we know that. Do we know what we're looking for? We're looking for what? dA over dt is our unknown when, Now, sometimes they give us a time, and sometimes they give us what the thing's going to look like when L equals W equals 10 centimeters. Okay? So what I've done is I've taken that entire, well, it's not a big paragraph, but I sure made it a lot smaller. Okay? You're going to look at dl over dt. Hey, that's length rate. dw is width rate, and d over dt I'm looking for when length equals width equals 10. Okay? Now, that's good to just collect all that stuff. Now, what's the formula that we should be working with here? Okay, these will always be your indicators right here. You got an L, you got a W, and you got an A. Because how are you going to get these if you don't derive things with L that if it doesn't have an L, W, and an A in it? Right? If it doesn't have an L in the formula, you can't do dl over dt. So what formula do you know would have L, W, and A in it? Length times width, right? So here's the formula I'm going to use. Area equals length times width. Okay, now let's just derive this. Okay, how do you derive this? So we got dA over okay, so what is this? What law? It's product law, right? Okay, that's why we spend this time together, so we can, right? But don't go dl dt times dw dt, because you're going to be like, kind of don't have w and l to put in it, right? So just make sure. So if I go the first times the derivative of the second plus the derivative of the second, or the second times derivative of the first, always puts my derivative in the second part of it. Okay, so that's pretty important that you remember to use the product law there. And once you've seen it once, and that's what I'm trying to say, when you start doing more and more of these, they do start to get, okay, a little bit redundant. This one's so nice, I got dA over dt already. Do I know the length? 10, right? So at this time, dA over dt equals 10 times 2 plus 10 times negative 1. dA over dt equals 20 minus 10, which equals 10 centimeters squared per second. Okay, therefore, the area is increasing at a rate of 10 centimeters per second, or centimeters squared per second, sorry, centimeters squared per second when L equals W equals 10 centimeters. Yep. Why did I? Because they wanted to know at that exact time what was happening. So they want to know what is the rate of change when Right. Okay. Ready to do a couple more? So we got a 6-meter ladder. He's leaning against the wall, and its foot is sliding away from the wall at a speed of 1. Can I continue here, guys? Because if I'm talking, you're not, right? Okay. Of 1 meter per second. Find the rate at which the top of the ladder is falling when the foot of the ladder is 3 meters away from the wall. Assume that the wall and floor are perpendicular. Okay, so we got a 6-meter long ladder leaning against the wall, and it is falling, or no, it's sliding away at 1 meter per second. We want to know at what speed is it falling. Okay, because it's going to happen at different, okay, when it's at a larger angle, it'll move way more on the bottom than it will be sliding on the top. If it slides 1 foot in the bottom, doesn't mean it's going to slide 1 foot at the top. Okay? If it was 45, a 90, a 45, 45, there you're going to find it very similar. But at the other times, you're going to find that they're very different. Okay? So, I don't know, let's draw a picture. Okay, so we got this. Okay, and then here's my ladder. Okay, here's my 90-degree wall. Okay, now are the distances on the wall and on the ground, are they changing as this ladder falls? Yeah. The height changes, the distance on the ground changes. What doesn't change as this falls? The ladder. Okay, so it's really important to know that this will always be 6 meters. Okay, and what's my ladder doing? It is sliding this way. Therefore, it's doing this too. Okay, just to get my own bearings of what's going on here. So, you know, this is what's potentially going on, right? Just so you can start to see that. Now, we do want to start putting variables on our, because this is going to be changing, and that's going to be changing, right? The height will be changing every time that ladder moves a little bit. Obviously, so will the distance away from the wall. So, the change, or the rate of change here, should be dx over dt. And this one here should be dy over dt, correct? Does that make sense? Okay, those would be the rates of change. Now, the question I would ask, what am I looking for? I'm looking for dy over dt is my question mark, and I know dx over dt is 1 meter per second. And when do I want to find out when? dy, okay, when x equals 3. Not y, x. So right here, this is probably the most important step. Like, you got to know what you're doing. You got to know what you're looking for. You got to even know what's happening. Now I need to relate x, y, and the ladder. Sorry? Yeah, that's an area formula. Yeah, I could go x squared plus y squared equals 6 squared, which is 36. So if you didn't pick out the 36 is going to stay the same. Now, I am not allowed to put in that 36 if it's changing, or the 6 if it's changing. But the ladder will stay the same length. But that's a whole other problem. Okay? Now, so before you start going, yep, x squared plus y squared equals z squared, right? This is my z. It's my hypotenuse. So 6 squared is 36. Okay? So let's just kind of get in that. Let's do the derivative right now. So what's the derivative of x squared? 2x dx over dt plus 2y dy over dt equals 0. Now let's just get this set up to solve. We want dy over dt. Okay? So let's just boot the other. So I'm going to leave 2y dy over dt here. And the other one, I'm going to move this to the other side. 2x dx over dt. So dy over dt should equal, oops, forgot my negative sign, negative. See the 2's coming to the other side, or underneath? So that's going to be negative 2 divided by negative 2 is negative 1. X, the y is down there, dx dt. Why is y in the bottom? Yeah, now we need y. You can see that we definitely need y. We know x is 3. Now you can find y using that snapshot in time. Because this is, so let's just call this a snapshot. This is what we got going on. It says when it is 3 meters away from the wall, what is the change? So that's not too tough, right? So we got 3 squared plus y squared equals 36. So y squared equals 27. Y equals the square root of 27, which is 3 root 3. So maybe because this is your notes, you want to start doing stuff like this. We'll call this like step 1. Step 2, grab all your stuff. Step 3, do the derivative. Step 4, do a snapshot. And then over here, step 5. Because when you look at your notes later, like which one did I do first? Like when you're looking just for empty real estate sometimes, it looks kind of confusing when you're done at the end. Okay, so now let's just put everything in. So I'm going to put it into this. So dy over dt equals, negative sign was there, negative 1 times 3 times dx over dt is 1, all over 3 root 3. Okay, these 3's will cancel, leaving me with negative 1 over root 3 And just to be consistent with math 32, let's get rid of the radical in the bottom. And this would give me negative root 3 over 3. Now, is that logical? Should it be a negative? Yes, it should. Yeah, it's going down. It's decreasing. Now, here's where you got to be very careful with your sentence. If you say, I'm just going to get rid of this equal sign, put it there. If you say the ladder is falling at a rate of negative root 3 over 3, is that correct? So you've put a double negative in there. You could say it's increasing at a rate of negative, but then that's weird too. Okay? So you that's where you want to show a bit of understanding here by saying the ladder is falling at a rate of root 3 over 3 meters per second when x equals 3 meters. Well, why am I already called it negative by saying it's falling. So it's falling at a rate. Now, how could anyone got away they would write this sentence and put negative? You could say the ladder is sliding down the wall, or no, because if you went down, right, it's just sliding at a rate of negative root 3 over 3. But if we see a negative, let's take it out of the sentence and call it decreasing, going down, getting smaller by, okay? Only if you want the marks. Yeah. Okay. Here's a gooder. A baseball diamond is in the shape of a square on the side. Mary starts running home from third base at a rate of 2 meters per second. At the same time, Steve runs from home plate to first at a rate of 1.5 meters per second. How fast is the distance between them changing after 5 seconds? Okay, so so let's kind of draw a diamond. So, oh, that's horrible. I can't draw a square and turn it. Yeah, maybe I can. I'll try it. Sometimes it's very inflexible, but I'll try it here. Yeah, I don't think I can. Let's see. Yes, I can. Boom. Yeah, I know. I want to see if I can move it first, though. Because you need as much room as you can get. Okay. Now, get the baseball diamond drawn. That's a good start. Does get harder than this, though. It's in the shape of a square, 27. So each one of these is 27.4 meters. Okay, and let's put home plate down here. This will be, call this first, second, third. Now, what's happening? Mary is here. Okay, the ball's hit, and she's going to run towards home base. Right, at a rate of, now, we'll talk about that in a second. Let's just kind of figure what's going on. And then we got Steve. He hits the ball. And he's going to be running at 1.5 meters per second. How fast is the distance between them changing? Okay, so what we're looking for, because when she's here and he's here, we're looking at this distance. Like, how is that changing, right, as they're moving? And you could see if they had a piece of string tied to the both of them, it's not going to stay consistent. Okay, now, anything else we need to, okay, let's figure this out. Now, what's that? Well, let's kind of see what we have first. Now, what we really kind of have to, this is where the little trick is Mary she's running in this direction, okay? So we do want to call that -2 meters per second. Okay, Steve's running up at 1.5 or 3/2, and that's going to be a positive. Now, but we got to, like, what is, you know, we've always been doing dA over dt, dL over dt, like, okay, well, yep, so we could say, just for us, we could say that dm, that's dm over dt, and this will be ds, not to mistake with. So do you see that we're calling this a -3 because this is the triangle we're going to be looking at. Now, Mary's always going to be outside. Her speed, this rate is outside, but do you see how this will be shrinking, getting smaller? And this side, as Steve moves, will be getting larger at 1.5. That's where the negative comes in. Okay, so that's pretty important to be able to see that. You're saying, well, but Mary's getting, her distance is getting bigger and bigger too. Well, we're not actually talking about the distance she's running. We're talking about the distance this triangle is changing. Or, sorry, the rate this triangle is changing will be in a negative. It's getting smaller. Okay, because as she gets over here and he's over there, you see how hers keeps getting smaller, his keeps getting, right? So we just want to keep track that that is going to be, the dotted line is my changing hypotenuse, basically. Okay, so why don't we call this our h, our hypotenuse. So we know that dm over dt equals -2 meters per second. And again, I don't think the negative would be as clear until I show the diagram first. We got ds over dt, that's 1.5 meters per second. We're looking for dH over dt at 5 seconds. So far making sense? Okay, how are we going to relate Mary, Steve, and that distance between them? Yep, Pythagoras, right? Because we know that that is a 90 on there. So we know that h squared equals m squared plus s squared. So let's call diagram 1. Okay, call this 2. And let's do a derivative. Because do I have all my information? I don't know. Okay, let's see. So I've got 2h dh over dt. So that'd be our third thing here. And then equals 2m dm over dt plus 2s ds over dt. Now this happens quite a few times when you use just the Pythagorean theorem, is you're going to get a bunch of 2's that you can just cross out. Everybody's got one? Cross it out. What are we trying to solve for? dh dt. So we have dh over dt equals m dm over dt plus s ds dt. And that's all going to be over h. Well, I divided it out right now. That's how I got this h down here. Okay. Now, there's a few things I don't have right now. I don't have m or s. Like, what is, so if this was s and this is m, okay, and h I don't have. Now, it seems weird at this stage. You're like 3 unknowns and we're not going anywhere with this one. Well, why don't we just do our snapshot? Because remember, if I was at this stage and I was really stuck and I still went and did a snapshot, you can get marks for your snapshot. Right? These are going to be worth a lot of marks. So let's just kind of take at this point right here. Oh, come on. So right there at that snapshot at 5 seconds, right? Here's my home base. So you can see I took that right from, that's H, that's S, and that's M. Now, the easiest one to figure out is, nope, S. Why is S so easy to figure out? It's 1.5 meters per second times 5 seconds. Okay, so for S, because we're doing, the snapshot is at 5 seconds. So that's 1.5 meters per second times 5 seconds. Steve has gone, how far? 7.5 meters. Okay, so now we know how far Steve has run at 5 seconds. What about Mary? Now, Mary, S equals 1.5, or sorry, 2, negative 2 meters per second times 5 seconds equals negative 10 meters. So, I've got this as 7.5. Mary's side would be what? See, Mary has done this. Does everybody understand that Mary has done that? So what's M? 17. Okay. This is where Mary started, right? She has run 10. So how much is this distance from here to here then? It's 27.4 is each side. So this must be 27.4 minus the 10 is 17.4. So 27.4 minus 10 equals 17.4 is that. So now I know S, I know M. We can find H. By good old Pythagoras, right? So H equals the square root of 17.4 squared plus 7.5 squared. H equals, what I got, 18.95. Okay, so that was number 4. 18.95, yes. So let's come back up here for number 6, and let's just put everything in. dH over dt equals, Mary is 17.4 times negative 2 plus Steve is 7.5 times 1.5 all divided by 18.95. dH over dt equals negative 1.24 meters per second. So at that point, the distance between Mary and Steve using capital letters is decreasing at a rate of 1.24 meters per second at 5 seconds. So as the ball, just before the ball is hit, how far are they apart? 24.7. Do you see? That's going to be their maximum, and then it'll happen again when they both get on base. Right? But any time between that will be a shorter distance than they always started out with. Okay? So it will be decreasing at that point. Lots of stuff to know here. Lots of stuff to keep straight. Lots of places to make mistakes. Got to make sure you're very careful. There's no doubt in my mind you will be helped a lot if you have the solutions out all the time, because at this stage it's very frustrating when you're learning and you made a mathematical error and you've done 5 steps with that error. You don't know, do I not know my stuff, or did that wrong answer just give me wrong answers throughout? Okay? So have that stuff out handy as you're going through it, and you will find that the more you do, and that'll be what'll show up on the test. If you're having no idea doing these, I can pretty well tell you it's because you didn't put in the work. Okay, so this is not going to be a fun time, but it's way, way, way less frustrating when you have the solutions out. Okay? Good?